Our next presenter is Prashanth Pandian, who is going to be speaking about NISAR Flight Software Architecture, and he's from NASA Jet Propulsion Lab. Prashanth.
Hey guys, I'm the flight software lead for the NISAR Flight Software, and I'll get into it here. Next slide, please. So the NISAR mission is pretty unique in that it's a partnership between NASA and JPL, and so that comes with some special challenges for the software. And I'll be going over the mission, the flight components, the flight software overview, and kind of the process that we adopted to use our heritage software and apply it for this new use. Next slide, please. So the gist of the mission is that NASA is building a radar, the Indian Space Research Organization is building a radar, and those two payloads are joining together on a Israel-built spacecraft. And the science objective here is a 12-day repeat track of the planet. So we are observing this exact same area every 12 days to see various deformations based on the radar data. Next slide, please. So the complication emerges when two different centers are working together. And in this case, we are providing half of the payload and Israel is providing the other half of the payload, in addition to the spacecraft with the ACS and GNC components. And so we have the symbiosis where both of our components need to work perfectly together in order for the spacecraft to meet its objectives. And I'll be going into each of these components and how the software addresses them. Next slide, please. So on the NASA JPL side, sort of our main compute element, our brain is called the PDS, or the Payload Data System. And here are some of the different devices that we've connected to. And on the other side of the spacecraft is the ISRO onboard computer here. And I haven't shown the B side components here, but there is another redundant half of this design. So these are the components that we have implemented on our side. So we have power distribution, pyros, GPS, our radar, radios, a solid state recorder for the science data, and these two large deployables that I'll get into later. Next slide, please. So the software architecture that we chose for NISAR was something that we wanted it to be something heritage that we could pick up and run with pretty easily. And so we picked the JPL sort of standard heritage flight software, which, as you can see here, has a long history. And I'm fortunate enough to be involved in the 2 boxes preceding NISAR. So I was pretty familiar with both the flight software, but also the processes. And you can see the software that we used for SMAP, which was also an Earth orbiter, was applied for NISAR and is being applied in SWAT and the DES radar. Next slide, please. So I'm not going to read out every bullet point here. It's more for your information, but most of you guys are probably familiar with this architecture. It's a priority-based, event-driven system where a task is essentially running on the processor and then yields the processor once its task is done. Processes communicate to each other via our IPC, and everything's statically allocated in terms of memory. And we try not to share memory between our software modules. Next slide. So modules themselves each have a single task, and as I said, they own the processor while they're running, and they swap around based on events or messages that occur in the system. Let's go to the next slide. So in general, the flight software architecture philosophy that we follow at JPL is sort of this layering system where we have our low-level hardware access layer where flight software modules talk directly to the hardware, and then we build on top of that. And the idea or philosophy here is that high-level behaviors don't have to talk directly to the hardware, and so we avoid coupling that way. And each module has, a set of functions that is dependent maybe on a module below it, but not beyond that. And certainly there's no upward linking to prevent cyclic dependencies. Next slide, please. So here's sort of a simplified software organization diagram. There's, of course, a lot more modules in the system, but this is meant to be more of a, I guess, a heuristic view. So in the bottom, you can see all the blue boxes here are the hardware. They're connected to various avionics components, and then they build up to higher level modules here. And you can see here the blue boxes are the highest level, including our fall protection, our modes manager, which is sort of controls the different modes that our payload data system is in, and the deployment executive, which is used to deploy those large deployables on the spacecraft. Okay, next slide, please. So how do we actually work on this flight software? So for the most part, we try to follow our heritage practices. And in terms of what did we change, we are now handling our software in Git. We've added in more static analysis processes. I think some of the earlier JPL presentations talked about how these tools have evolved over time, which has revealed new issues in the software. And that's definitely one of the issues that we had to deal with, and how we addressed the evolution of the tools as opposed to the static, heritage software. We tried to leave things as best we could, unless we thought that it was going to be an issue moving forward. We do nightly builds using Jenkins, and we also autocode a fair amount, our command and telemetry, and we also use Magic Draw UML state charts for our complex state machines. And one important point here is that we've inherited this code from previous missions, and along with that comes our inherited tests, which saved a lot of time in terms of getting the software up and running for this smaller team. Let's keep going. So going back to autocoding, we have HELIX, which is a web-based dictionary platform. And so the development process that we follow is that our system engineers can go in there and put in commands and telemetry. And we already have this autocoding process in place in which we can export directly from the dictionary manager, run the autocoder, and it's generating all of our headers and our C code for handling commands. And then, so once we've autocoded from that, it's easy for us to go in and do the actual implementation. And then we follow the process backwards to make sure that we're staying in sync with the dictionary. And when it comes time to release the dictionary or release software, we then audit the dictionary against the web platform and verify that everything matches. Next slide, please. So our autocoders are where we really benefited from SMAP sort of forging the way here. So we can take things directly from HELIX, which is the web platform, as I mentioned. It's also a database of our commands and telemetry. And we can export the XML directly from there, run it through these Python autocoders, and generate our .c and .h files. In addition to that, we have our magic draw diagrams for our advanced state machines, which also export to XML and go through our JPL Statechart Autocoder to result in our .c and .h files as well. Next slide, please. So the next couple of slides here are how we've applied some of these things to NISAR where we hadn't maybe not done in the same way before. So one of the things is the Statechart Autocoder, which we've been using for several missions here. So you can see, so we keep the Magic Draw UML files in CM, and we basically are only modifying the model within CM. So whenever the model changes, we then re-autocode. And that code is then tested and checked in. And where this is really beneficial is we have software, like, for example, the higher level software executive modules like the modes engine is built on a state chart. And so for previous missions where we may have had a state chart, we can reuse those state charts and then modify them to whatever needs to change for NISAR. Next slide, please. So our testing overview and strategy. So we have two levels of requirements. You guys are probably familiar with, lowest level of requirement is the unit test level. So we're using the unit test to verify software requirements, and we're using GCov to analyze our code coverage. So those unit tests are also inherited from the previous missions. So things like low-level drivers, for example, have already previously been vetted, and we don't need to do too much to get those up and running and working. Whereas new modules, for example, GPS, we would be writing new code for, and of course, the corresponding unit tests. And the other level of testing that I really want to mention here is what we call our FIT test, which stands for Flight Software Integrated Testing. And this is sort of our black box testing, and the idea is that this is sort of halfway between a software test and a system level test that might be done by a system engineer. So we use the software in addition to software simulation and also actual hardware in terms of the RAD 750. But the main goal here is to test software. So we're still sending commands and looking at telemetry, but we're not, for example, calling functions directly. And I think that this level of testing has been a huge boon for software in terms of finding bugs early on before we have delivered. Next slide, please. So the process that we followed is also inherited from SMAP. So the test team and the software team and the software lead, myself, are involved in coming up with these test plans and then executing the test plans, doing the data reviews, and then we deliver these data test results along with our software release. Next slide, please. Yep, so we're just going through the process here. The important thing here is at the end, when we do our run for records against our software releases, we also identify for each test which requirements are being tested, how, and what other level 6 they also tie to. So if we deliver this artifact to systems, they can then use that to figure out how they should structure their tests. Next slide, please. We also had simulation support equipment, which is sort of a simulation of VxWorks that we can use to test our software before it meets the hardware. And again, we were able to inherit, with some tweaks, the SMAP implementation for this. And this also saves us a lot of time in debugging issues before we have to get on a hardware test bed where time may be limited. Next slide, please. Okay, so the next couple of slides here are sort of a deep dive into some of the software modules that we use on NISAR and how we were able to adapt them from SMAP. So I mentioned earlier the modes engine is fully inherited from SMAP. And so basically the only difference that we had to do was use a different subset of modes. Now on the SMAP orbiter, they had ACS and GNC and those types of modules. And so the modes engine was quite complex, whereas on NISAR, on the JPL side, we're not responsible for keeping the spacecraft in the air. So our modes concepts are a lot simpler. Now, when we went to implement modes, we can just take the old Statechart Autocoded XMLs and the diagrams, and then just simplify the diagrams and re-autocode the XMLs, which allowed us to use the same somewhat complex modes engine without having to deal with the complexity, since most of it had already been vetted by SMAP. Next slide, please. So some of the things that made it easier for us in the modes engine is between each mode transition is a mode action table. And this mode action table enforces the power states of devices and asserts various flight software states. And we were able to implement all these things purely by updating the Statechart UML diagram. Next slide, please. So this is a mode diagram of the NISAR modes, which are a lot simpler than the SMAP modes. And the way the modes engine works is, we boot into a mode and the ground can command to go into different modes, which then allows various activities. As I mentioned, the deployment is a pretty big part of the mission, and so it gets its own mode. And then for the most part, we're just sticking in a nominal science mode. If we have any sort of issues, we drop down into safe mode. For the most part, it's a pretty simple process. Next slide, please. So deployment. So one of the major parts of this mission is just deploying this 6-meter mesh reflector. And this is probably the most complicated Statechart that we have for NISAR, and it's also something that's completely new. And the deployment is consisting of 2 phases here. So there is a 9-meter boom, and then on the end of that is a 6-meter reflector. So there's first we deploy the boom, which is pretty simple, and then we deploy the reflector. Next slide, please. So the boom deployment is pretty simple. We weren't able to utilize any heritage here because there was a different deployment method on SMAP. But for the most part, the boom deployment is pretty simple. It's a discrete set of ground commandable steps. So it didn't involve any sort of state machine or anything like that. The reflector, on the other hand, is pretty complicated. It's consisting of a lot of mechanical sensors and deployables within the reflector. But we were able to convince our systems engineering team that this is a good application of our existing state machine autocoder, and so they sort of formatted this into a flow chart for us that we could easily implement. Next slide, please. So the other major high-level component of NISAR is the fault protection engine, which again we were able to completely inherit from SMAP. So the way the fault protection engine works is different modules have different faults that can occur. When those faults occur, they sort of have a fault announcement to the fault protection engine, and then the fault protection engine carries out system level responses. And let's go to the next slide, please. So this is sort of a diagram of how these system fault monitors worked. So if, for example, in this diagram, we're monitoring a temperature, if we're under the allowable temperature, we're in a green state, which no action, and then we go to a yellow state, which is sort of a telemetry state that says, hey, we're now in yellow, but we haven't taken any action yet. And then the black state here is if the sensor, for whatever reason, goes offline and we get a data outage. And then if the error persists in the yellow state for a certain amount of time, we then enter the red state, which then announces the fault to the fault protection engine, and the fault protection engine can then take action. Next slide, please. And within the fault protection engine, there are idea of tiered responses. So for example, if you have a fault that occurs that has higher criticality than a lower level fault, that fault response can bump the lower level fault. And in addition to that, responses can call sub responses and so on. Next slide, please. So the inheritance for this was pretty easy in some terms, and with respect to the engine. For example, the engine didn't change at all. The ideas and concepts behind the fault announcement, the responses, and the application to system modes all stayed the same. So what we did change, though, is since it's a completely different system, there's a completely different set of monitors that had to exist in the system. But fortunately, there is also an auto-coding process for ingesting monitors, ingesting responses, and mapping them. And so we were able to greatly utilize the existing SMAP pattern for that to implement fault protection for NISAR. Next slide, please. So in summation, the NISAR flight software team was a lot smaller than previous teams on the initial diagram that I showed you, but we were able to keep to the same software standards. And the reason for that is the strong inheritance of not only the modules and functionality that we had, but the patterns and the engines that we used. And so I think one of the things that we used in our initial proposal for NISAR was not just inheriting the code, but inheriting the documentation, the testing, the process, and most importantly, the people. So some portion of the team is already familiar with the patterns, et cetera, which allows us to continue with the same process without too much perturbation. And throughout the process, we tried to minimize change from the previous heritage applications by building on top of the patterns that already existed and not by changing the existing ones. And next slide, I think that's it. Any questions?
Yeah, it looks like we have 3 questions on the Q&A. All right, the first one from Tyler Whitaker. Are there any publications regarding the state machine autocoder?
I think there are numerous. I can get that to you. There are several papers I know of, but I don't have them on hand.
Okay, maybe you could throw those in the Talks Slack channel when you get a chance.
Yep, I can do that.
Okay, all right. Next question from Nicolo Battazzati. Did you find any limitation in developing state charts graphically? For example, when they become complex with more than 4 to 5 states and different conditions? So multi-part question. How do you cope with possible faults that happen during the state chart execution? Maybe I'll read the rest of the question after that, after you get a chance to answer that.
Yeah, I'm looking at the question right now.
Okay, all right.
So I think, so one of the things that I really wanted to highlight is that SMAP and previous projects have really vetted the JPL state machine autocoder quite a bit. And in addition to that, other projects are currently using the same Statechart autocoder, and there's a good community of users here, so we communicate with each other quite a bit. And we have found issues that we've been able to solve, and I do agree that as things become more and more complicated, there are more different conditions that we have to evaluate. But fortunately for NISAR, we've been able to keep that complexity down because, as I said, it is a simpler system than the previous missions. And I see here you're asking about, do state machines try to mask faults? So as a philosophy, we don't have that automated. So if we're going to execute something that's going to utilize the state machine, for example, modes, all of that masking and unmasking of faults has to happen as part of a ground sequence.
Okay, and Tyler Whitaker asked another question: is the fault protection mechanism tied into the autocoder system?
So there's two different autocoders here, so I don't want to confuse them. The Statechart autocoder is specifically for state machines, whereas the fault protection autocoder that we have it autocodes essentially lists of monitors to responses to modes. And connects that flow together. So I guess my answer is yes and no.
Okay. And then one other question, pretty open-ended. Any thoughts on comparisons to CFS?
I have looked into it, but I don't know if my answer I can answer in the short amount of time I have here. But I can chat with you on Slack about it.
Okay, and then I didn't mention that there was Lee Garbs.